Okay, so let's continue our discussion of multiple regression model estimation. This is class number 12, and it's second part of multiple regression model estimation. Okay, so before going to more details about what are the assumptions in multiple regression model, what are the differences between MRM and SRM, I want you to introduce to a topic called Venn diagram. And most probably you guys are already familiar with what is Venn diagram, but in very few textbooks people talk about how we can use Venn diagram in order to cover the intuition of multiple regression model. So this is nothing scientific, and so you should not cite me in this, but at the same time, I'm quite confident that it's going to help you a ton in terms of understanding what's behind of some of these interpretations of or the relationship between variables in multiple regression model. Because if I only go over the mathematics, sometimes it becomes very confusing, especially if I don't go over the proofs. But using Venn diagrams is going to make it a lot more easier. So for now, let's talk about some terminology and basically how we can apply the Venn diagram visualization in terms of better understanding the multiple regression model estimation. Again, this is going to become a very useful tool down the road when we cover more challenging topics in regression analysis in general. All right, so let's begin. Uh, as I said, again, most probably you guys know what is Venn diagram, but we're just using some circles and shaded areas, and let's clear some terminology. These are the arrangement that we make with each other. Again, I just emphasize it one more time. This is not scientific. This is something that one of my professors taught me, I think, 10 years ago, and I really love the idea. And I no, it has been super helpful to my own students, and I'm gonna pass it to you guys as well, and hopefully you're gonna enjoy it too. Okay, so remember, this was our simple regression model, right? Regressing y on only one variable. So imagine we have two variables, y and x. And let's say that the black circle represents the variation in y, right? So for instance, if I have some circle like this is variation in y. If I compare it to this, or maybe this, so basically the more variation you have in your data sets, we make this circle bigger and bigger, right? So that's simple. So let's imagine each circle is a variation in y, the black circle here. The red circle is, imagine it's represent the variation in x, right? So we have a variation in y, so we have a variation in x. Again, just to give you some reference, imagine this is your wage, and x is your education. And we're talking about the variation in x. Okay, imagine it's a circle. It should not be necessarily a circle. It can be any shape. But for the sake of argument, let's imagine it's a circle. The bigger the circle, the larger the variance of of your variable, right? Now, what's the goal in econometric analysis? At the end of the day, you want to explain this variation in your wage, right? And basically, you're going to use another explanatory variable and hope that this other explanatory variable is going to able a chunk of this variation in y. So that's the idea, right? Hopefully, then again, we hope that the larger this area, the better. For instance, if it is y, if it is x, that's awesome, right? Because the majority of the variation in y is explained by x. This is a very good model. This is, again, maybe I'll talk about the specifics, but let's say we prefer this model, this one, to this one. And let's say imagine y and x are not correlated with each other at all. So again, we're going to start with a model that's, none of the coefficients are going to be end up significant. Basically, if the data is something like this, x and y are not correlated, it's not going to help us using that x as an explanatory variable in the model, right? All right, so We know what is black circle, what is red circle, and then now let's talk about this red shaded area. What is this? What does this red shaded area represent? And guys, don't get confused. We just say it represents four different things. It doesn't mean that these four different things are the same. Obviously, R squared is not the same as beta hat 1. It's not the same as correlation between X and Y and SSE. But we say that this red shaded red represents all of these things. And it's very intuitive, okay? Let's start with the SSE. What is SSE? We say, okay, this red shaded area is a representation of SSE, sum of the square of explain. What part of the variation in Y is explained by X? What's the answer? Red shaded area. We're good. It also represents correlation between X and Y. Again, these are some arrangements, agreements that you are making with each other. So what's the correlation between X and Y? Again, this red shaded area is a representation of that. We are not talking about numbers at all. Whenever I use Venn diagrams from now on, I'm not talking about the numbers, the specific numbers. We cannot assign any numbers to that. But we can talk about the magnitude. So for instance, if it is a small or large, right? Then think of R squared. R squared, this red shaded area is R squared. The larger this red shaded area, the better news. It means that your X is explaining a bigger chunk of your Y, the variation of Y. Does that make sense? So we can think of it as R squared. And finally, we can think of it as beta hat 1. Remember, what was beta hat 1? Beta hat 1 was something that estimated the relationship between your X and Y. So if this red shaded area is larger, so it means that the beta hat 1 is going to be more and more relevant. What does it mean? It means that it has more explanatory power to literally quantify the relationship between X and Y. Okay, so that's one thing. This is a red shaded area. Now let's talk about the gray shaded area. Let me use another color. Let's talk about the gray shaded area. So the gray shaded area, we can think of it, again, it's a representation of SSR, sum of square of residual. What was sum of square of residual? You know, the part of variation in Y which is not explained by the model, right? So we can think of it as SSR. We can also think of it as sigma square, noise. Whatever is not included in X, do you remember? Whatever is not included in X, we just call it U. And if the variation of that thing is this. This is the variance of U. And then finally, we can think of it as sigma hat squared. Because, sigma square is not observable. The observable version is sigma hat. So this is basically the variation of residual. Okay. So again, the gray shaded area is a representation of these numbers. The red shaded area is a representation of these numbers. And this doesn't imply at all that these numbers are the same. Not at all. We know for a fact that SSE is different than R squared, different than beta hat 1, different than correlation. And also SSR is different from sigma squared, different from sigma hat squared. But we are going to make this arrangement with each other that let's think of these shaded areas like these things, okay? It's going to help us a ton. So, and we're going to use them interchangeably. So sometimes I'll look at this shaded area, I call it R squared, sometimes I call it beta hat 1. But all you're trying to do using Venn diagrams is to make the intuition a lot easier to understand when we go forward with multiple regression model, okay? So that's one thing. That's this shaded area, and so far we talked about simple regression model. However, from now on we want to talk about multiple regression model. What does it mean? It means that you don't have only one X. You have a couple of X's, X1 and X2. Again, it can be X3, X4, X5, and etc. Right? Now let me talk about correlation versus partial correlation. Some of you guys may have heard about these two terms, but for some of you which is new, just pay attention. Correlation, we have talked about it a lot. So when I say the correlation between X and Y, basically I want to see if they move together up and down And we know the correlation is between -1 and 1. If it is 1, they're perfectly correlated. If it is -1, again, they're perfectly correlated, but the sign is different. If the correlation is 0, literally they're not related to each other, right? The correlation, they're not linearly related to each other. So for instance, here's an example of correlation between y and x is equal to 0. Here's the example of correlation between x and y is very close to 1 or -1. It really doesn't matter. Again, we are not talking about the sign or the number. All we care is some sort of the magnitude, so if it is large or small. Okay, so here the correlation is big, here the correlation is small. And in simple regression model, we said all we can get out of a model is basically the correlation. Okay? And most probably it's going to remain correlation going forward, because we're not controlling for lots of other experimental variables. Okay, so that's one thing. Another thing is that we deal with in multiple regression model is something called partial correlation. Partial correlation is different from correlation because it controls for other experimental variables. So let me explain what I mean by that. So partial correlation, in multiple regression analysis, we deal with partial correlation. In simple regression model, we deal with correlation. So let's read this one. Partial correlation between y and x1. So between y and x1. There's a partial correlation, and it's defined as the correlation between y and x1 while controlling or netting out the effect of x2. Okay, so if I use this Venn diagram, y, x1, y, x1, right? So what is the correlation between y and x1? This is a correlation. Now if I add another variable, what is the partial correlation of x1 and x2? I have to net out the effect of x2. So say this is my x2. If I want to net out the effect of x2, I can imagine, you know, let's completely drop x2 out of the picture and see what is the pure effect of x1 on y. And what's the answer? The answer is going to be this new shaded area, only this part, only this part. This is called partial correlation, only this part. So partial correlation between x1 and x2 is this. Partial correlation between partial correlation between x1 and y is the one on the left, and partial correlation between x2 and y is this one on the right. Okay, so this is what we're going to use in multiple regression analysis. So it's very important. One more time. Simple regression, at the end of the day, what you get is correlation. Multiple regression, at the end of the day, what you get is partial correlation. Okay. All right, so with that, let's look at our multiple regression Venn diagram. So let's say we have 3 variables in the model, x1, x2, x3, and again, these are all hypothetical. These are circles, right? I just draw them like this to just show you how it looks like. If that's the case, for instance, if the variation of y and x is like this, and x2 is like that, and x3 is like this, right? So let's say this is the model, and we want to use Venn diagram to say something about beta head 1, beta head 2, beta head. If x1 is this one, x2 is this one, and x3 is this one, then you can talk about basically you can figure out what are the beta head 1, beta head 2, beta head 3 in the data. Remember, in multiple regression analysis, beta head 1 represent the partial correlation between x1 and y. Beta head 2 represent the partial correlation between x2 and y, and beta head 3 partial correlation between x3 and y. What does it mean? It means that if you want to look at the pure effect of x2 on y, you have to net out or control the effect of x1 and x3. Okay, so we say that, do you remember that interpretation that we went over last class, holding all other exponential variables explicitly constant? What is the pure effect of, let's say, x1 and y, right? So if that's the case, we are going to call this part shaded area beta hat 1, this part beta hat 2, and this part beta hat 3. And OLS, so this is going to be very important, guys, pay attention. When OLS is calculating beta hat 1, beta hat 2, beta hat 3 for us, it's going to throw out this part of the data. This part of the data is not going to be useful when OLS is doing the estimation. Why? Because that's, that's the joint, let's say, so this part is a relationship between x1 and x2, and when we're talking about beta hat 2, beta hat 2 is the net effect of x2 on y. So if I want to see the net effect of x2 on y, I have to net out the effect of x3 on y. Okay, so that's why OLS is going to throw out this part. For beta hat 1, well, x1 and x1 is not, there's no overlap between x1 and x2 and x3, so OLS is going to have easy time. Say, you know what, it's already clear, it's not contaminated with x2 and x3, so all this shaded area is going to be effect of x1, the net, the pure effect of x1 on y. And so if I hold x2 and x3 constant, it really doesn't affect this part. What about x3, beta hat 3? Beta hat 3 is going to say, okay, this is x3. What is the net effect of x3 on y? So it's going to be, again, net effect is going to be only this part. So it's as if I'm holding x1 and x2 constant, okay? I hope that this makes sense. And again, we're going to draw lots of Venn diagrams. And at the end of the day, I promise it's going to make your life a lot easier. So try to have fun with it. Let me actually, I don't know, draw a couple of other ones. So imagine this is my y, this is, well, actually let me do it on the whiteboard, it's easier. This is, if this is y, x1, I'm trying to draw better circles, yeah, x1, let's say x2, and then maybe x3. This is more realistic in the world because usually all the variables that you're controlling, x1, x2, x3, at the end of the day, they're related with each other. The correlation is not zero. Again, think of y as wage, and maybe x1 is your education, x2 is your experience, x3, I don't know. I'm trying to come up with something which is maybe tenure. Well, not, maybe age. Yeah, age is a better one. Okay, let's say this is our example. Obviously, there's a relationship between education, experience, and age. So the correlation is not zero. So there's going to be overlap between x1, x2, and x3. And these three collectively want to explain, well, what is the variation in y, right? So what part is not explained? This is the unexplained part. So this is obvious, right? Maybe we call it maybe sigma square, the unexplained. Again, these are the representations. And when I want to look at the pure effect of x1 on y, basically that's the partial correlation. We say if education increased by 1 unit, holding experience and age fixed, what is the net effect of that increase in wage? So how do I show that? Basically look at x1 and y and make sure that you highlight the area which has zero overlap between x2 and x3, because we're assuming that x2 and x3 are fixed. And then what is the pure effect of x1 on y? So this is going to be my beta hat 1. And let's actually use another color. What is beta hat 2? Again, what's the net effect of x2? What is the partial correlation between x2 and y? This is the partial correlation of x2 and y. This is my beta hat 2. And finally, where's beta hat 3? So for beta hat 3, it's going to be a little tricky. So I have to make sure that there is no overlap between x3 and x1 and x2. So let's pause for a second and see if we can find that area. Okay, were you able to find that? No, look at that. If I want to hold x2 fixed, so it's as if this circle, I have to get rid of that circle. If I want to assume that x1 is fixed, So I have to get rid of this circle as well. So do you see any overlap between x3 and y when we are fixing x1 and x2? So here it seems that the answer is no. So what does it imply? It implies that OLS is going to have a very hard time finding beta hat 3. Because guys, remember, OLS is going to throw away all the overlap data between x's because it want to make sure that its ceteris paribus interpretation, multiple regression, it's going to fix some part and look at the net effect of, let's say, x1 and y, x2 and y, x3 and y. So it's going to be have very hard, no, OLS is going to have very hard time pinning down this beta hat 3. We're going to see that, you know, the variance of beta hat 3 is going to be very large at the end of the day because OLS is not able to find the right data to do the estimation. Okay, so this again, usually most of the time when we put many explanatory variables, so what happens to the model is that OLS is going to have maybe harder and harder time, especially if the x's are very correlated with each other. So we call that problem multicollinearity problem, and we're going to talk about it in very detail later on. Okay, so one last thing that I want to talk about is the ideal world. So what is the ideal world? So we hope that if this is my y variable, I have a variable that I want to explain. We hope that we come up with some x1, x2, x3, something like this. x1, x2, x3, maybe x4, oops. Yeah, let's say x4, and etc. Right? We hope that this is our utopia, very ideal world. We can find variables that are not correlated with each other, but they are correlated with your target variable, which is y. If I find these 4 variables out there and I'm trying to estimate, you know, the relationship between, I don't know, the x1, x2, x3, x4, and y, it's very good news, right? So all these red shaded area are the explained part. So collectively, these are the SSE. And the only unexplained part here, again, in this simple example, is going to be here. So maybe our SSR is a small. Okay. So again, this is very ideal, but we know in real world we don't deal with that. We usually deal with something like this. So real world. This is our real world. All right. Okay. Now there's a section in the textbook that if you want to just read it as the way it's presented, it's very confusing, and it's called partialing out and interpretation of multiple regression. And now with the help of Venn diagram, it's a lot easier to go through it. Again, so these are the 2 steps of the partialing out interpretation of multiple regression, but I'm going to walk you through using Venn diagram and see how helpful these Venn diagrams are down the road. So it says that one can show that the estimated coefficient of explanatory variable in a multiple regression can be obtained in 2 steps. Step number 1, regress your explanatory variable. Remember, it says that regress explanatory variable, let's say x1, on all other explanatory variables, let's say x2 and x3. And again, for simplicity, I'm going to say let's say we only have 2 explanatory variables. So let's say this is our model, y, x1, x2. We know that at the end of the day, what is beta hat 1? Is this. And we want to show that we can get to this beta hat 1, which by the way, it's the partial effect of x1 and y controlling for x2 using 2 steps, right? So basically at the end of the day, I want to get to this shaded area, but in 2 steps. We already know the intuition. It's the net effect of x1 and y. But let's see if we can get it in 2 steps that the textbook is talking about. So step number 1, regress your explanatory variable, let's say x1, on all other explanatory variable. So we are regressing. I'm trying to mimic the scale that we have up there. So imagine this is our x1 and x2. So regress x1 and x2. Okay. Then regress y on the residual from the regression, from this regression. So let's talk about where is the residual from this regression. I'm regressing x1 on x2. Again, x1 on x2. Where's the residual? Can you show me where's the residual in Venn diagram? As a hint, if I regress y on x, where's the residual? Here's a representation of residual, right? Or the variation of residual, resid. So when I regress x1 on x2, where's the residual? Here's the residual. This part of x1, again, if I'm regressing x1, x2, this is going to be the residual. This part of the variation of x1 is not explained by variation of x2. Okay, so this is step number 1. Step number 2, regress, let me use an autocolor. Regress y on this residual. So let me add y here. This is my y. If I want to regress y on this residual, and now, again, when I say this residual, I want you to completely forget your x2, right? So we are regressing y on this blue shaded area. Do not look at x1, do not look at x2. Just look at y, the red circle, and this blue shaded area. Okay, so it's something like this. I'm gonna draw it and erase it, but so it's going to be, this is my y, this is the blue shaded area. If I regress y on this blue shaded area, which is my residual, then what's the relationship between the two? That's it. So if I want to show it here, I'm talking about this shaded area. And we call this shaded area partialing out and beta hat 1 interpretation of multiple regression. So these two are the same. I want you to see that for yourself, that these two are the same. Okay. We already knew that using Venn diagram, this is a partial relationship, a partial correlation between x1 and y. We are netting out the effect of x2. But the textbook is saying that you can do it in 2 steps, and these are the steps. At the end of the day, we get the same answer. So this part is the same as this part. Okay. But I guess using Venn diagrams, you could clearly see that why these two are the same. Okay. I think not using Venn diagram, this is going to be very confusing. But now I hope that at least it's less confusing. So why does this procedure work? So this is important. Why does this work? The residual from the first regression, guys, remember, what are we trying to explain? We want to say that the effect of x1 on y is the partialing out effect. It's the net effect of x1 on y, no controlling for x2. The residual from the first regression, okay, we're talking about this blue shaded area. The residual from the first regression is this one, this blue shaded area. Is the part of the explanatory variable that is uncorrelated with the other explanatory variable. So it's a part of x1 which is uncorrelated with x2. Does everyone see that? That this blue shaded area is not correlated with x2? This is obvious, right? This is not correlated with x2. Okay. Then the slope coefficient of the second regression. So slope coefficient of second regression is what? So let me write it down, or when you watch the video. So this is, the first one is talking about this. The second one is talking about the red shaded area. Again, I try to keep the scales the same, but maybe it's just a little bit bigger. The slope coefficient of the second regression, beta hat 1, therefore represent the isolated, the net effect of explanatory variable, this is our x1, on dependent variable y. Does everyone see that? This is very important. And again, at the end of the day, you don't need to be worried about these Venn diagrams or all these steps, but the intuition is very straightforward. This is the thing that I told you earlier, even without going over these things, right? I said that, let's go back to our whiteboard. If you have a regression, if you're regressing y on x1 and x2, if you want to see how you interpret beta hat 1 is only this part. Why? Because it is the pure effect of x1 on y netting out the effect of x2. How do I net out the effect of x2? Numerically, I literally hold it fixed. So that's our beautiful interpretation of multiple regression model, right? Explicitly, we can assume that this is fixed. So I can literally get rid of all this thing. I can assume that this is fixed. If I fix the x2, I can assume that the variation is gone, and then I only focus on this one. So all I see is this. Okay. At the end of the day, we're focusing on this green area, and then the overlap between y and x is here. All right, so this is called partialing out effect of, or partialing out interpretation of multiple regression analysis. Okay, and let me quickly go over these couple of slides. We're going to pause here and continue by starting the assumptions. So, goodness of fit measure for a given model. This is, you know, if you remember from simple regression model, we know what is goodness of fit. We looked at R-square for goodness of fit. For multiple regression model, exactly the same procedure. What are the equations? Even the equations are exactly the same. SSE divided by SST, SSR divided by 1 minus SSR divided by SST. And the relationship between SST, SSE, SSR is the same as simple regression model. At the end of the day, total variation in y is defined as sum of square of expected, sum of square of explained part, and sum of square of residual, which is unexplained. So, and again, the definitions are exactly the same. So for instance, what is the explained part? Summation of y explained by the model. So it's y hat I minus y bar to the power of 2. What is the unexplained part? Literally our residuals, y minus y hat. Oops, sorry. Oops. Okay, y minus y hat to the power of 2. What is the total? Y minus y bar to the power of 2. Again, everything is the same as simple regression model. So done. And alternative expression for R squared, we have already seen this. No, and actually in the previous class, the part 4, I did the calculation for you in R, and I emphasized that this is not equal to the correlation between y and x to the power of 2. Why? Because which x are you using? x1, x2, x3. Okay, so if you want to see the numbers, just watch the previous part 4 of class 11. So there I went over the R scripts and showed you an example. Okay, so again, nothing new here. We already know these equations. All right, then we look at an example. Again, this is repetitive. We regress college GPA on high school GPA and ACT, but this is an important part. So how do you interpret the R square? The R square, this number basically suggests that high school GPA and ACT collectively together explain about 17.6% of the variation in college GPA. If I want to use Venn diagram for that, so let's say this is my college GPA, this is my high school GPA, and absolutely, I think you guys will agree that high school GPA and ACT has some overlap. So let's say this is the case, and again, this bar is going to be my beta head 1, this bar is going to be my beta head 2, and maybe so let me show you the R square. R square is the explained part collectively. What part of the variation of college GPA is explained, right? So let me use maybe blue. So collectively, this part of the variation is explained, right? And again, you'll get to use to working with Venn diagrams, and I want you to trust me for now. Again, if it seems a little confusing, overwhelming, just stay with it, and it will become a lot handy down the road, because you know the concepts are getting will get a little more challenging for chapter 4, 5, and etc. And in those for those topics and chapters, we definitely need to go over the intuition using Venn diagrams. All right, so let's stop this video. I'm gonna see you in the next one when we cover the assumptions, you know, basically Gauss-Markov assumptions, not Gauss-Markov assumptions for multiple regression model. See you then.